Explaining why you have been given a Jolly Rancher candy. So the talk is about glass, and the Jolly Rancher candy is like the household glass. It's basically sugar in an amorphous form. And so I invite you to conduct a silent experiment while I'm talking here, which is to let the candy dissolve in your mouth very slowly without chewing it until it gets rather thin. And then at that point you can bend it with your tongue. Maybe you have had that experience before. You should do it carefully. You can push it against your teeth or whatever, against the palate of your mouth. Do it carefully. So what happens is the following. Here is a phase diagram, which is a scientific thing. And you know that much of the food has to do with phase diagrams. And the important line in here, so what we're looking at is like a mixture of water and sugar. So the solute in this case is the sugar. I just grabbed that from the web. There's a number of those. And this diagram is a eutectic, which is something that has a melting point minimum. So the important lines in here is the one from here down to that place, and then it goes up to the other side. That means here you would have pure sugar. Here you have pure water on that side, right? So you can look at the melting temperatures of pure water, which is 0 degrees C, and then pure sugar is way up higher. That's sort of more like 100 degrees C or around that. And then if you mix the right amount, about, excuse me, 2/3 of sugar and 1/3 of water, then you get the lowest possible melting temperature, which is about minus 9 degrees C. That's sort of like the recipe that you use in order to make ice cream. There's additional components that go into that, but that's what you're basing on the fact that you can make this ice cream, or that you can have this suppression. Now, on top of that, forget about all the rest of it. The other important line is this one, which describes where a glass forms. So when we go to the equilibrium phase diagram up here, you take like a composition, say this water sugar solution, and you quench it down to a low temperature, like minus 20 degrees or something like that. Then in principle, if you wait long enough, you get ice crystals and sugar crystals. But if you quench it rapidly, then you get a glass, right? And the Jolly Rancher is somewhere over here. There's about 2% water in that. And what we see here is now, if you cool this down and you do it fast enough to get below this line in temperature, so this left axis is the temperature, you get below that, then it doesn't crystallize anymore. The kinetics or the motion of atoms is arrested, slowed down to the extent that it no longer allows for the construction of crystals in the material. So then you get a glass, and that's what is called the glass transition temperature. Now when you take the Jolly Rancher into your mouth, then you heat it up from room temperature to about 37 degrees or 35 degrees. You also infuse it with some more water based on your saliva. That means that you end up somewhere around here in the phase diagram. And at that point it becomes, it's above the glass transition temperature, meaning that the material can be worked, or the way that the glass manufacturers call it, it's above the working temperature. And so that's where you can see the softening of the glass when you have it in your mouth and you gently push it with your tongue. Eventually it will bend. So I'd like to switch to this overhead projector if it takes a moment. So here's the Jolly Rancher. In its original form, it's a glass. Here's a candy that I prepared, it's like a cooking show, right? So ahead of time, I did that. It's about this tall, this small when you are able to bend it, and that has to do just with the thickness of it. But now it's cooled again, and I don't know whether you can see that, I can break it brittly. Right, so it's a glass again, so it has it's brittle fracture at this point. So so you can do this. You see the softening, or you feel the softening when you have it in your mouth, and if you're patient enough to then take it out and wait until it's cooled, then you can break it without, and so it doesn't bend anymore. So that's sort of like a demonstration of the glass transition. We go from the glass to above the glass and then go back down. So now I'd like to go back to my presentation, which I wasn't paying attention too much. All right, so the phase diagram. Enough of that. What I'd like to do is introduce glass based on its history, and kind of go along a timeline where we have like different achievements that we can accredit to the glassy state of material. That would not have been, so discoveries and technologies that would not be possible without it. And it starts sort of in the early years, in the prehistoric days, when the forms of glass that were known at that point were obsidian glass, which is a volcanic glass. It's just whatever comes out of a volcano, it solidifies into a glass. That means it doesn't crystallize. And then you can break it, and you get sharp edges, and you can use that as tools. Such as like arrowheads or knives or chisels that you can use for carving or for hunting. And after that, there's another form, which is the fulgurites, which is the fossilized lightning. Those are discovered in like the Sahara Desert, where lightning strikes the ground and it heats it up momentarily and cools off again, and it gets a phase. These don't look very nice, but it sort of like shows the electric discharge, so it can be showing some branching or whatnot. And when you analyze that, you also find that those are glass. So those were the original forms of glassy materials. Then in Mesopotamia is where the glass manufacturing started. So this started during the Bronze Age time when, that's right. In the Bronze Age, people did metallurgy, so they were extracting copper and zinc from ores and melted it into utensils, weapons, you name it. And of course, one of the byproducts is slags, which is kind of a glass. And so then they realized that they can cast those melts into molds and form objects, and then maybe later even sort of like drill these objects with tools and create jewelry. Right, so that was the days of the Bronze Age, which goes roughly from about 2,500 to just before the birth of Christ. So the origin of glass manufacture took place here. There's also in Asia that people discovered glass probably independently, or it was transmitted. But then from here, from Mesopotamia, it migrated into Europe, and the nation or the realms that propagated the distribution of glass was the Roman Empire. Proliferated the use of glass, and they also discovered, actually in Syria, they first discovered the glass blowing process, which is something that we do until even today. And it was allowed us to create objects like containers, drinking vessels, and ornaments to a large degree. And so the Romans were distributing glass technology over the entire realm that they had. So it went over most of Europe, at least southern Europe. Took a little longer to get to Britain and northern Europe. There's an anecdote that is recounted by Pliny the Elder and also by Petronius. These were written down in around 4th century, but the events are alleged to have happened at the realm of Tiberius, who reigned between 14 and 13 AD. And the story is such that one day an artisan came and got an audience with the emperor. saying that I'm going to demonstrate something to you. I'm going to gift you this vessel, a glass vessel. And Tiberius said, "Oh, great, thanks." Then he said, "Can you hand it back to me? I'll show you something." And so he took the vessel and threw it on the ground, and rather than breaking, it just was dented. And then he took some tools and he sort of molded it back into the original form and handed it back to Tiberius. So Tiberius contemplated the situation and said, "Does anybody else know how to make such a glass?" And the artisan said, "No." And after that, Tiberius had him beheaded and his workshop destroyed because he had his money in metal. And here we are today complaining about like having to write proposals to the National Science Foundation. We're not risking to be beheaded. So in those days, research and progress was much more perilous, I suppose. The Romans propagated this, and I'm fast forwarding now around 1100, 1200, when artisanship in Murano or in Venice was up the rave, and they fashioned like glasses that were very colorful, and they were even used as a currency, so these are trade beads. There's some more shown here. They were very ornamental and very pretty, and they were bright and colorful, and so they were especially used in countries that were being discovered, like explored, where populations did not ever see anything like that, not even a regular glass. And so they took it as currency. They traded for whatever goods that they were trading it for. And the story with the glassmakers in Murano, the skill to do all of this was a secret at the time, and they were moved in 1200 something. The workshops from Venice were moved onto the island of Murano. There they had to reside. They were not allowed to leave, and if they were to leave without approval, they didn't have non-disclosure agreements in those days. Apparently they were hunted down and killed. So that's how precious these recipes were. That brings me to the topic of color of glass, and I'm just going to touch the tip of this. So there's like different ways that you can color glass. The most common one is by using different chemicals. Right? So the transition metals, which is a group of metals that are in the middle of the periodic table, if you know what I'm talking about. So there's like the irons and the manganese and the nickel, things that we have in common steels or even other metals in our daily experience. They have two oxidation states, typically. They can even have more, but typically they have between 2+ and 3+. That means the 2+ is stripped of 2 electrons, the 3+ is stripped of 3 electrons. And there's a mixture of the two. And when you shine light on this, then the light excites the electrons to go from 2+ to 3+, meaning that it gets stripped away from the metal cation at that point. And that requires energy that's being absorbed from the light, and so the color that's being generated is basically by removing other colors. And so we have, like the green glass is something that we use iron to create, and then there's the brown glass that has, I'm blanking now, nickel, and there's the debate, of course, between whether the beer is better being contained in a green bottle or a brown bottle. Anybody know the answer to that or has a preference? Which beer tastes better? Green? I think brown has it. Brown has the majority, and I'm with them because brown sort of absorbs more of the UV light that would destroy the flavors or whatever the molecules that are in there. So if you make a choice in the future, I mean, that's also why the medicinal vials are typically dark brown, to keep the light out and keep the medicines unaltered. The other main technique, and this is something that they discovered way in the past, they didn't really know it at the time, is metal nanoparticles. So it's not just a metal that's like part of the network, that's like dissolved as an atom in the material, but it's like a tiny particle that's of the order of 2, 3, 5 nanometers. And they have a large surface area compared to the bulk, the volume of it. And so there's a lot of surface on there. And so you can excite what's known as surface plasmons, which is a similar thing. You just excite electrons into some vibrations and it absorbs light again. So it's a similar mechanism, but it's more intense. It's more intense just than dissolved atoms. So if you have these nanoparticles, and that gives, I mean, what's best known as the ruby red or the ruby red glass, which is filled with nanoparticles of gold. And people knew that back in the medieval times, or in Murano. They knew it even before that, or actually they generated and didn't know that they did that, but there's glasses that are older than 12th century or 13th century that have gold nanoparticles in them. So that's the second most prevalent. So that gives rise to and you can use different metals to get different colors. So that gives very vibrant colors. And then the other one that I want to mention, there's a few fringe ones, but the one that you may be familiar with is the opalescence of glasses. So opals are gemstones that are being found in nature, and the way that they produce these colors is by creating what's termed microphase separation. That means that you have one glass, and then you form tiny droplets of the order of microns, so 1/1000th of a millimeter, that are distributed in the glass rather regularly. So at least in certain domains, and then you create what's known as a photonic crystal. A photonic crystal has the property of like letting some color of the light go through and other color blocking it, so reflecting it. So what you see from these gemstones is light that's being let through or that's being reflected in a certain way. Right? And that has to do with these photonic crystals, which we are now using to create devices for telecommunication and computing. So from there, I fast forward to the 17th century, which is a century that a lot of stuff happened in that century. That's when Newton lived and when the scientific revolution occurred, where sort of science, and Galileo came at the beginning of that. So Copernicus was actually in the century before that, but where the wisdom was decoupled from religion. Right, so that people were able to explore concepts independent of the doctrine that was being preached to in the cathedrals of the world, and that happened and so this is my own interpretation. It happened in England for the most part, because in England different royalties were succeeding in rapid succession, and each one of them, or they alternated in what the doctrine was, right? Like either Catholic or Protestant, and so I guess the smart people at the time saying, "Oh, they can't really decide. Maybe we should not even listen to it. Let's go explore independently." So a part of the reason why this was important. It's also important economically. In those days, they sort of formed a modern monetary systems. They issued bills for payment because when they went to pay with gold, they got robbed. But they went to pay with letters that said, "I guarantee that you can have this if you need it." Bills. Then they weren't robbed. So that was another thing. But what created like the difference was windows. So especially in the northern European countries, in the winter time it was dark for oftentimes, and even during the day it was cold. So if you didn't have the money for windows, and windows existed since the medieval times, but they were typically given to the royal palaces or the knighthood, the knights and church and things that were drawing from a larger community in order to create these habitats. But the regular artisan and merchant, they didn't have windows yet until about the 17th century, when that became prevalent. And so the windows allowed for having daylight come into the room to do like whatever, write bills or make contracts or study things that fabricate things that had to be done indoors. And they could work longer hours, and they were in the comfort of having like daylight and being able to see what they were doing. So that's one aspect that sort of like started the economy in these countries. Then the second thing was, of course, so here's like a picture of that. I mean, older windows, like the cathedral windows, the one in the center is at the Cathedral of Notre Dame. Those existed for a longer time, but the one on the right, that was sort of a window that was fabricated a typical window fabricated in the 17th century. And you see, it's not very clear, the glass. Right? It was not something that you said, oh, I'm just going to watch now the birds fly by. It was just to get light into the room. I mean, even the Romans already had, like the rich Romans had windows that were glass, but you couldn't see through them. They were like for small windows, and they were basically just decorative. Here now, there was a light that came through, and you could work around the year in all seasons. Now, the way that glass was made in the days was that the Romans invented glass blowing. That gives you like a vessel or a bulb, and you can kind of cut it and open it and fabricate like a container. That was like the typical thing. But the main way that they would make window panes was to take one of these blown bulbs and then pierce it at one end. That's sort of the second picture, like going from left to right. The second picture, somebody cuts open the bottom of that bulb, and then the other person heats it back up and then spins it. So the fourth pane is spin it until it becomes a disc. And this disc was apparently measured up to 15, 18 feet in diameter, so just at height of the person's mouth, and then to the floor and above. So that's what they were able to do. And they spun it out using centrifugal force, and obviously the glass would not have even thickness, because at the edges it's going to thin out more based on that centrifugal force being larger. But this is the way that they made it. They let it then cool off and cut pieces out of that went into window panes. Right? So the windows always had these lead cames to put the windows in, but that's what they did. They also had tried technologies to like roll sort of like a dough pin made of rock over, pour it on a table and roll it out, but that was not so prevalent. Another technique was the one on the right, where they took this bulb and elongated it into sort of a cylindrical tube, and then cut it open lengthwise, heated it up, and then let it fold again. So on the bottom right, you see that it's sort of like the time evolution. So then gently folds up if it's at high temperature, and you get like a flat piece of glass. So those were the two main techniques to make glass for windows. And the other thing that, of course, propagated or that advanced us was optics. There's the telescope that Galileo used. That's, I believe, a replica of it. There's Hooke's microscope. So Hooke is the person that, if you have heard of Hooke's law, which is if you apply a stress, then the elongation is proportional to that stress, and the constant is called the elastic constant. And Hooke was, it's called Hooke's law, that he was the one that discovered that. But that's not the only skill he had. He also discovered the cell. He was the one that first reported on the fact that plants are made of cells. And then there was the epidemic that took place in Britain, and they all moved to the country, all the scientists at the time, including Newton, Hooke, and others. And then they looked for things to do, because they couldn't like do their usual thing in the city of London. And they probably put everything under that microscope that they could find, and even like tissue from skin or whatnot. And he also found that the skin has cells. The telescopes, of course, allow you, or the binoculars or monoculars allow you to do exploration more swiftly. I mean, if you can sort of gauge where to land with your boat, if you explore a new continent, then that was an advantage. Another thing that sort of was introduced at that point, it doesn't really mean technology, but these Prince Rupert drops, and I have some more information about that as we go along. This is it looks like a tadpole, has like a bulb at the end, and it has a long tail that's scraggly. We'll show you actually a video of how they're made. And if you have that Prince Rupert drop, you can bang it with a hammer at the tadpole at the thick end. You typically don't break it. It's not unbreakable. It's not as strong as diamond, but you have to smack it really hard in order to break it. And the reason why, I'll explain in a little bit. So this was something that they apparently discovered in Germany. It's named after Prince Rupert of the Rhine, who then gave it as a present to King Charles II of England. He then handed it over to the Royal Society to study why it does that, and so they were doing research on that. And much later, the principle on which this is based has become important for the technology that I'm going to end up with, which is strong glass. Before I get there, I talked about church windows, and I talked about the fact that they are all put into like this framework of lead cames that hold little segments of glass. And when in the modern days, when people had to repair such a thing, they noticed that the glass was typically thicker on the bottom. You may have heard of that myth that it was explained that the glass was put in this window in the 12th century or the 13th century, and it had like 7 centuries to droop down, to flow, right? And so that's an explanation that oftentimes is given. That would mean that the state of glass, which is at this point I have not really gotten into what the glass really, what this amorphous state of matter really means, but I'll end up with comments on that. But this would mean, and was one explanation, that glass is nothing but a liquid that has been, the motion of the atoms has been slowed down so much that it takes centuries for it to flow. But other than that, if you just wait long enough, so if you measure this on the geologic time scale, it would be similar to like a glass that flows on a minute base. But there's now evidence, so there's like a illustration of that the bottom part is thicker. So at this point, I'm going to get out of this presentation and go to show you, that's not the one I'm trying to show, this one. This is a video. There's pitch tar is one form of amorphous material, but it's a little bit complicated. It's not just that it has tar in it, it has also olefins and some liquids that are dissolved in it. But people, you can take a piece of pitch tar and you can smack it with a hammer, it breaks brittlely. But if you put it in a funnel and you wait about 10 years, is there any PhD student in here that is now getting worried? Then you find that this drops. And the first of this experiment was done in Australia. This one is in England. And the Australian one, they had this was started 80 years ago. Now it's probably like 100 years ago. They had this contraption, but they didn't have a camera 80 years ago that could keep track of it. So for the first 80 years, they missed the drop. So they came in, or the day before it was just hanging like that, and then they came the next day, it was falling down, and so they were not able to witness it. And then of course, with time-lapse cameras and batteries that last, there's another problem. Batteries didn't always last long enough for this, but here's now a video of this falling down. It's a time-lapse, so you see the clock spinning on the right, and it's sort of like it's going over hours, but at some point it's just sort of detaches, and it's the same material that if you put it on the table and you drop it, you smack with a hammer, it breaks brickly. In this case, it just falls down. So that's kind of like giving weight to the idea that the glass is nothing but a supercooled liquid. Oh, sorry. That's not what I want. All right, so, but what determines the flow of glass is the parameter called viscosity. You're probably familiar with viscosity. The engine oil that you put in your car has a certain viscosity rating depending on whether you live in Scandinavia or in Spain or whatnot. You take a different one. And the viscosity is studied. The viscosity of glass forming system has been studied for about a century now. So the modern glass science, quote unquote, that we have started around the 1920s. And one of the things that we discovered, or scientists discovered at the time, was that the viscosity has a peculiar behavior. So in plotting the log of the viscosity, the logarithm of the viscosity, I'm having like orders of magnitude instead of like linear scaling, versus the inverse of the temperature, the reciprocal temperature. And then normalize it with respect to the glass transition temperature. The glass transition temperature, I'll get to back later, is sort of the temperature at which the glass stops flowing or can no longer be worked. So it's the rate of flow is so slow that it's considered a solid at that point. It turns out that, and you can also measure this thermodynamically, looking at things like the heat capacity, and I'll show you a diagram of that in a minute. So it turns out that, for one, all glasses, whether they are candy or whether they are a silicate glass, which melts at high temperature, their viscosity at the glass transition temperature is 10 to the 12th Pascal second approximately, give or take the error bar for the measurement. And so they're always the same. And the other thing that's peculiar is that what one would expect based on kinetic theory is that the viscosity should change along this line here, which is, when it does that, it would be called Arrhenius behavior. Never mind, let's just say that that's what we expect, but what we find is that they droop down. The viscosity has sort of like a much more rapid decrease with increasing temperature. So I go to the left, I increase the temperature. And that seems, or vice versa, if you have a liquid that you cool, then the viscosity increases at a rate that's unexpectedly high, right? Which may explain why it doesn't crystallize, because the viscosity increases so fast as you decrease the temperature that it doesn't allow for a crystal to form, which requires some atomic motion rearrangement. So the viscosity now allows us to do simple calculation. And I think I have an equation on here. I'll disguise it in terms of words. That the Newton's law of viscosity, obviously we had to wait until the 17th century to get this law, is that stress is equal to the viscosity times the strain rate. That means that the change in length or the changing thickness relative to the original thickness, if you divide this and you apply a force, and that force divided by the surface area gives you the stress, you divide it by the viscosity, which is a quantity that you measure. And we know now that the glass transition temperature is 10 to the 12th. Below the glass transition temperature, it is higher than that. And anyway, you divide the stress by the viscosity, and then you get the strain rates. You multiply the left-hand side by time, then you can solve that for time. Means that you can calculate how long it would take for the glass to thicken by, say, a millimeter. These church windows that were thicker at the bottom. And there's a recent study, actually not so recent anymore. In 2008, they did very careful experimentation on how to extrapolate the viscosity from the glass transition temperature, which is up here. All right, so that's the glass transition temperature. Now going to lower temperature, you could continue this line, but that would shoot up really fast. And there's probably something else that happens, so there's some creep that occurs. And so they did measurements, and they found that at room temperature, the viscosity will be 10 to the 25th Pascal second. Right? And that's the best value that we know about what the viscosity could possibly be. And so if you put that in the equation, then you find out that it takes 1 billion years to change the thickness of the window by 1 nanometer. So it's not a thing for a PhD study to study, but that means that this can't be explained. So the thickness of the windows at the bottom cannot be explained based on flow. And your guess is as good as mine. I'm giving you a possible explanation for that. I mean, artisans made these windows, right? So they cut the window and then they put it into these cames. And they probably put the thick end to the bottom, the heavy end to the bottom, which is a common thing to do. So that's my explanation for it. But the other thing that I'm showing here is the heat capacity. So the specific heat is something that measures the amount of heat that you would be able to absorb in a body or in a material as you change the temperature. So if you increase the temperature, you store more heat in it. And the specific heat means that it's the change in heat in the body divided by the change in temperature. And what we see in that at TG, glass addition temperature, there's peculiar behavior. There's on heating, you find this little cusp. That means that suddenly when it changes from a solid to a liquid, there is some additional amount of, or additional rearrangements that take place that would allow the materials to flow as a liquid coming from a glassy amorphous solid state. On the way down, it sort of just has this turnover, just a change in the viscosity. The reason why I'm showing you this is that I mentioned earlier that the glass addition temperature is kind of defined relatively narrowly. There's some wiggle room, depends on the cooling rate, but it's relatively narrowly defined. So that means that if we get 10 to the 12 Pascal second for the viscosity at the glass addition temperature, it's not just based on the fact that the instrument that we measure viscosity with doesn't function beyond that. It's that you really have, like, we know that this is the glass addition temperature, right? Based on additional measurements. All right, so fast forward to 2008. No, not 2008, like the 1970s. That's when optical fiber telecommunication was coming into place, that the telephone lines that go across the Atlantic were, the new ones that were installed were optical fibers. And they're thousands of kilometers long. What you do instead of transmitting an electric signal, you transmit an optical signal. So you have a transformer or a modulator that transforms the light into the electric signal into a light signal, and then it propagates along the optical fiber, and then eventually it fizzles out because thousands of kilometers still has like some optical resistance for light to penetrate through that. So typically we have, like, every 50 kilometers there's like a little box that does the magnifies magnifies the signal again, and then it continues. But 50 kilometers is pretty far. So that's from here to Lansing, something like that. So that's one continuous fiber, and of course it has to be drawn. That we developed the technology for that. But it also has to be very pure, the glass that you use for this. So it's essentially silica glass with some additions to it, but it has to be very pure. Give you a comparison. So semiconductors that are used, like the silicon chips, they are based on a semiconductor silicon that has been solidified into a big crystal block. Then you cut slices of that. That crystal block has impurities of 10 to the minus 6. So 1 in a million atoms is an impurity. So that you have to refine it, the silicon, to the extent that you can do that you have that high purity. Otherwise, your transistors would not function well. For the optical fiber to be working, you have to have 1 in a billion atoms as an impurity. So you have to reduce the purity even more. So it's actually a process that takes a lot of patience. Typically, you deposit, you take a big glass tube and you deposit chemically silica in there using like salt gel, or a reaction that has silica as an acid, and then it condenses and you basically have like a silica powder. Then you heat it up, it frits down, and you get the solid glass, and then you draw it out into a fiber, and you can go up to as long as you wish. The technology is there to do that. So the reason why we have the ability to transmit signals optically in fibers is based on total internal reflection. And it's a little bit hard to see, but hopefully you can follow along. Total internal reflection is based on the fact that there's an interface between two media that have different refractive indices. The refractive index in a nutshell, or in a simple approach, depends on the number of electrons that are per unit volume. So the denser the material, the more electrons in there. Light interacts with electrons when it goes into a glass or a crystal, and it slows the light down. The more electrons it has to interact with, so the denser the sea of electrons that it has to kind of like displace, I mean, it sort of transmits into like an oscillatory field, the slower the light goes through it. So that's characterized by a refractive index. So the refractive index of vacuum or the ambient air roughly is 1, and then anything that's a solid has a refractive index of higher than 1, which reflects the fact that you slow down the propagation of light. So that leads to refraction, and you're all familiar with the straw that sticks in a water glass. It looks to you that as though it was kinked. And if you didn't know how this works, I'm supposed to do physics here, right? So here's my favorite way of explaining refraction. We're coming with a light beam that goes in this direction. The lines here are supposed to indicate like the wavelength of the light, like the maximum between, or the distance between two maxima in the wave. And it hits the interface, and then everywhere where this edge here hits the interface, I'm drawing a bunch of circles. They may be a little bit hard to see. And then what I do is, so the distance between this is the wavelength, and it's reciprocal to the velocity. So it's proportional to the velocity. So if the light is slowed down, then the wavelength gets shorter. Right? It has the same color, but it has a shorter wavelength. And when it comes out, this may be now air, or it may be like a material that has a lower refractive index, a lower density of electrons. And then I sort of like draw lines from the edge here, and then what I do is from each one of these edges where these touch, these wave maxima, let's say, touch, I'm drawing circles. And the circles are spaced, you can best see it on this side, they're spaced in the amount of the wavelengths of the next medium. So this is a longer distance between the waves, and that means that you have a faster velocity, that means a lower refractive index. And for an optical fiber to work, that's what you have. You have the center has the higher refractive index, the cladding that's around it has the lower refractive index. Then you can get this total internal reflection. So when I draw now from each one of these points where they touch, a line that touches the circle in the next place, and the next one goes over, touches the second circle. Let's see, the second circle here. The third one touches the third circle, and so forth. So I'm putting a tangent on that. Then I get the wavefront that is generated in the new medium, because anything in between is being eradicated by interference. So that would sort of give us the kink. Here you see that these vectors that are, again, like these vectors are perpendicular to these wave maxima. Those represent the propagation direction of the light. And you see that how this refraction occurs would just be based on the distance between these circles that are being touched. And that's expressed in terms of Snell's law, which tells us what the relationship between these two angles here. Right? So you see that in this example, the light that comes in from the bottom that forms the angle theta 2 with respect to the surface normal, to the perpendicular to that surface, is smaller, so it's closer to that, so the angle is smaller, and then it bends over when it goes into the medium with the lower refractive index. Right? So I've now created like a little animation of this, and I first have to start it. So we have roughly this picture here, where the Snell's law applied to two vectors. The red one is again the one incident to the interface, and the green one that comes out on the other side. And if you continue that now, then you see that the green one bends down and eventually goes parallel to the surface. That's the critical incident angle. And anything beyond that cannot go through the material. It does not go in the other, and so you get this total internal reflection in these angles. And this is the moment when we show a demo of that, actually two demos, not just like computer graphics that you can do anything that will work. So here's a tube of plastic polyacrylate or something of that nature, and I'm using a laser, and I'm going to first put like this laser here. Well, you see that it's already giving like a total internal reflection, and if I go closer to the axis of the direction of the axis of then you see that I have, especially at the beginning, you see how the light is being bounced off the outer wall, and it comes back in, and then it sort of like spreads out. It's diffused, so the optics is not quite clear. The angle spreads out, and the reason is that this tube of plastic has been bent into a spiral, and that means that the outside of the spiral here has a lower density than the inside. It means you make some kind of an optical component. It's not a straight, it's not homogeneous, so you have some kind of a lens effect. That's why it starts to diverge, but you see that the light goes through. The other demo is the one here, which I've never done myself before, but I have to turn this on carefully so that nothing gets misaligned. There's a light that comes through it. So there's a bottle here with water in it, and it has an orifice, a small hole. The laser goes in through one side and comes out through that hole. So it's aligned with that. Make sure it's really the case. And when I open this cap, the light flow comes out, and you should see does it actually go in there? The big light.
Try to hold it, and there's the hole. All right, go ahead.
There. All right. Thank you, Monica. So whatever math we did here works, apparently. All right, so that allowed us to do optical telecommunication, and of course that has its benefits and that you're familiar with. Oops. I want to spend a moment on glass making. I think I have enough time. This is a schematic of a glass furnace. So here comes the raw material, which is sand and some whatever rocks that we put in there. It goes into a furnace, and the furnace looks something like that on the inside. So it's like a big pool, and above the pool there are torches that burn fossil fuel, and they heat up the glass based mostly on radiation transmission. So they heat up the entire lining of insulator in that furnace, the refractory material. And it heats up the glass, and then once it's liquid, it flows out. It goes through this nozzle here, and then it falls onto a tin bath. So this is not easy to see, but sorry, is this actually, yeah. So actually I'm not really showing this. Oh, I'm going to have to do this. So there's a tin bath in here. That's the so-called Pilkington process, where they figured out that the best way to do this is have the glass be poured onto a tin bath, and the glass is lighter. It has about the density of 2.5 grams per cc. Tin has like 5, 6, or 7. And so it just falls on top, and then it spreads out. They actually have like little rollers on the side that sort of stretches it out. But then you let it go through here, you pull it, and by the end of this, tin melts at a lower temperature than the glass transition temperature is. So it's solidified, and then you cut it and you have these window panes, and you get a very flat glass because the bottom is like rendered flat by the tin bath. It has contact with it, and the top is just based on gravity. It flattens out. So that's how we make glass, and it's a continuous process that goes on essentially indefinitely until something breaks and it has to be repaired. Which brings me to the next thing. So here's actually a picture of one of these glass furnaces. It looks pretty red and yellow, but if you focus on it, you can see that the edge of the bath is about here, where it touches the wall. Here are these burners that throw flames out, and you see the reflection of the flame, right? So even at like 1600 degrees C, you would basically have like a pool with a liquid in there, and it has all the properties that we know of liquids at room temperature. Now, you recognize this structure here, which is the new entrance to the Louvre Museum in Paris. And you can see that the building here is visible through the glass. That was a stipulation of the curators of the Louvre Museum. I mean, these entrances were made because the tourist flow was so large that they couldn't use the regular doors. And they said, if you build this structure here, it has to be translucent enough that you see all the beauty of the old buildings that the Louvre is in. And that means that you have to have a glass that's pretty transmissive optically. And that typically means you have silica-rich glass. Silica melts at 1700 degrees Celsius. So it's really hot. And the cost of this glass used in these pyramids is an undisclosed amount. I know because when I was in Paris, I worked for the company that made the glass. And what happened was that they said, see, what happens is that when the glass is transparent, it doesn't reflect as much. The heat just goes through the glass, or the glass liquid, and hits the floor of the furnace, even at that high temperature, right? The resistance or the transmission is pretty high. And so the company, I'm not going to name it because I don't want to make an advertisement here. The company said that to make that glass, we have to essentially destroy a furnace. And then they waited out, and you see what happened. We have that structure. So they destroyed the furnace in doing that. But that shows you that the property, that the transmission of silica glass is pretty high, even at high temperatures. All right. The last station in our chronicle here is 2008, when Gorilla Glass was invented. And that sort of changed like the picture of technology that we know. So we have devices like our iPhones. I can drop it, it won't break, but I'm not going to do it. So means that one of the big drawbacks of glass was glass fracture, right? Glass was useful, except for that guy that went to see Tiberius, that he had it all figured out. But other than that, you had all these beautiful structures, windows. It would break when you drop it. So there's this fragility that's associated with glass. And so I'll talk a little bit about glass fracture. Glass fracture, here's like kind of a fiber cross-section of a glass fiber, not an optical fiber, just a regular fiber, breaks always this way, and this is also common for other brittle materials, is that there's a flaw somewhere at the surface. That's where the crack starts, and then it has sort of like a very smooth surface to begin with. That's what they call the mirror. Then there's like a mist around that mirror, and then it becomes what they call a hackle. And the crack starts here, and then you impart energy into the material when you apply a force to it, and you displace the material, you strain it, and that is storing the energy. But it's more energy than the system can store just by straining, so it creates surface. Surface has a cost of energy as well. And as you create this, initially it says, okay, I have a certain amount that I need to get rid of, so I'm going to make like one crack that's flat, has like a very well-defined surface, but then the system figures out that, oh, it's not enough, there's still more strain that I have to release, and so I'm going to make the surface rougher. That means I have a larger surface area per change in radius, and then eventually it just gets starts to panic, and it creates like this very rough surface, and there's more surface energy in that. Also, the crack velocity increases in whatever this radial direction going away. So it's like starts slowly, and then it accelerates to form more surface and more rapidly. So this is what happens, and it's in glass. It's always the surface, and there's never a glass that breaks from the center unless there's a cavity in there to begin with. And the way that's being illustrated, so people draw fibers, researchers, the ones that started in 1920 and after, they draw fibers, and the moment that you draw it, you can measure the strength, and it's pretty high. And then after a day or after a week, after a month, that strength has reduced. Because what happens, the glass surface is exposed to environment. It could be like mechanical, that it's being rubbed against something, it's bent. But typically it's the environment, the humidity in the environment. The water is very aggressive to glass surfaces. And so you create these small imperfections. They're magnified here. And you say you have a fiber that is like, 2 feet long, and you determine the strength by pulling it, applying a stress to it or weight to it, and you get a measurement, and that measurement would tell you, oh, it's this much. And so it breaks here because that's where the largest flaw is. So the weakest link is where the largest flaw is. You take each one of these segments, you pull that, you get a higher strength. So you go up this, right, and the smaller your segment is that you have left, you pull it, it will always break at a higher tensile stress than the fiber before, the segment of the fiber that you had before. So you get what's known as the Weiser statistics, which means that the more experiments you make, the higher the strength becomes on the same material. So you have to be aware of that. But the point here is really that the surface flaws are the killer for glass stability. So the glass always breaks at the surface. The other thing that it does, if you so I have another video, so that's going to be more commercials, I'm afraid, but let's see whether I can just change to this. Let's go to this. So there's an experiment that people do in their home, which is called the cavitation experiment. Oops, sorry, I have to actually go out of the presentation. All right, so I'm going to play this video, and what happens is this guy is going to smack the bottle with a rubber mallet. So it's not using an object that's very hard. It sort of just induces a momentum pulse that goes through the bottle, through the glass, but also the bottle is filled with water. And you'll see what happens. And then there's a slow-mo that follows afterwards. So immediately the bottle breaks, and here's the slow motion. I'll do this in. So what happens is that there's bubbles that form, cavitation bubbles. Let's make sure that that's Right. So the bottle goes down because he has the impulse, and you see all right, that went too fast. So let's try one more time. It's earlier than that. So you see the bubbles form. They're cavitation bubbles because the water goes up, or the bottle goes down, but the water doesn't follow immediately because it has its own inertia. But then it's kind of stuck to the bottom, and the bubbles now collapse, and the bottle breaks. And what I'm trying to point out is that the moment it breaks, it breaks around the rim here, and it actually starts there. So that's where the first crack occurs, and it kind of shoots this way and that way. Now, what happens? I mean, the explanation that's typically given is that the cavitation bubbles, they're basically water vapor. They collapse more rapidly, and so they kind of give an extra force on the bottom. But the thing is, the same impulse has been given to the bottle when it was smacked with a hammer. Right? It sort of absorbed that without problem. The water was the one that didn't absorb it, so that sort of came later. And the bottle didn't break the moment when it was pushed downward, because there was a compressive wave that went into the bottle wall. Once it was stable and the water cavitated on it, that exerted a tensile stress on the wall, because the impulse from the cavitation collapsing pushes it down, and the bottle breaks on the side. Right? It doesn't push out the bottom itself, or in the center of the bottom, it breaks at the side, wherever the glass is under tension. So glass breaks typically under tension, it never breaks under compression. And that's the thing to also keep in mind. Let's see. Right. So it breaks under tension, and you see where this is going. The surface flaws, they're also under tension, and so they're being exasperated, or they're being amplified. A short anecdote about glass fracture. You recognize this person, Jacques Cousteau, the ocean explorer and nature conservatist. He was inducted 30 years ago into the French Academy, and he said that, and as one of the tokens that people get when they get into the academy is they get a sword. All the members of the French Academy have a sword. And he was a sworn pacifist and decided, I'm going to refuse the sword. I'm not going to be associated with a weapon that can harm. And so they figured out that the way around it would be if he gets a glass sword. And so he ended up with a glass sword. And the idea would be that before he can do any harm, the sword will break. Right? So that was good enough for him. But these days, I guess we have stronger glass, and that sort of is no longer necessarily the case. Let's see. Okay. I never talked about the structure of glass because it's actually difficult to ascertain. We know that crystals have a regular structure. That's the big difference between glasses and crystals, is that glasses are randomly organized. They're not completely random, but they're disordered. Right? So there's a pattern in there. There's like the diamond on the right-hand side, but the left-hand side looks like a hot mess. Like there's like disorder in there, but the bonding is like still preserved. There are certain bonds that are between certain elements that are prevailing. But so when you form a glass, we've already seen the picture of the specific heat. On the left, you see the specific heat that explained before. If you compare that with the crystal specific heat, that's the blue line on the bottom. That specific heat has a certain value below Tx, which is the crystallization temperature. The glass transition always occurs above the crystallization temperature because it can't reach it. Never mind. When something crystallizes, there's a spike in the specific heat, because think about the cube of ice that melts in the glass. The glass maintains the same temperature, and you have a finite amount of heat that goes into the melting of the ice. So there's a spike, and whereas so it's going to infinity essentially, the specific heat at that temperature, but other than that, it's like a very narrowly defined process. The other thing that I want to show is the specific volume that we have for a glass formation. Those are the red and the green line on the right-hand side. You lower the temperature coming from the high temperature melt, and you see that the thermal expansion coefficient, which is the change of the specific volume relative to the change in temperature, is large. That means things shrink by a large amount. Then you go through the glass transition temperature, and it starts to shrink not so much anymore. Right? And that's important to keep in mind for what's coming next. I'm going to skip that one. There's like a couple of mechanisms of strengthening glass. One of them is glass tempering, which you're probably familiar with. The window glass in your car is tempered glass. And the way that you do that is by taking the glass and heat it to just above TG, the glass transition temperature. And it's homogeneous at that point. Then you quench it. You immerse it into a cold bath of water. And what happens is the outer skin starts to go through the glass transition temperature. It shrinks a little bit, but then it sort of stabilizes, and it becomes a layer of rigid glass on the outside, whereas the inside is still can still flow. And what's important is it contracts more because it's still on the branch that has a larger expansion coefficient. So that means that by the time you're done, the outside defines the shape of the glass, the inside defines the density, if you will. So the inside is now being subject to tensile stress because it cannot shrink the way it wants. And so the inside has under tensile stress. That means that puts the outside under compressive stress. What that does to the flaws is that it basically closes the flaws. And let's see. Yeah, it closes the flaws on the surface, and it even if you were now to bend the glass to break it, you still have to overcome that compressive stress in the surface layer before the flaws start to open up, so you get the higher strength. That brings us back to the Prince Rupert drop, and here it is shown seen through cross polarizers, because the glass that's under strain exhibits birefringence, and you can essentially see these color changes as like iso stress curves. Like it's the highest stress, compressive stress on the outside, and tensile stress on the inside. I'm going to show a quick video because it's always satisfying to see things break if it's not your china or your glassware. All right. So there's this outfit called Smarter Every Day, which I'm just going to, there's the play button right here. Oh no, this didn't work. Sorry about that. I queued it up, but apparently it refreshed anyway. So they're making a Prince Rupert drop. They gobble up some glass and let it drop into a bucket, and it is quenched. It solidifies rapidly. It takes more time in the center, but what you get out is this tadpole. And the next thing is they're going to bang it with a hammer. He's explaining that it's going to happen. So they knock on it. It doesn't break. And then he dares him. And sorry, it isn't. There. So he knocked it hard enough. And this is filmed with a high speed camera. So in this case, it broke. And it didn't break based on the hammer being hitting the tadpole, but it was because at the end of the tadpole, the little filament broke in his hand, and then the wave of fracture propagated into the tadpole from the end. And that's basically the way that it typically breaks. So here are some shots of, they pinch the end of that long filament, and then you can see the wave propagating. So they pinch it there. This is a fast movie, and there's a slower one. And you see how the wave of fracture propagates from the end of the tadpole. It's easier to break it there than in the thick end. So you get the idea. I encourage you to visit Smarter Every Day, and you can see that on YouTube and watch it at your leisure. So this is like the slowest. But it's based on this fact that the tensile, the compressive stress that is exerted from the tensile part of the inside is preventing preventing the cracks to be opened. That's one method. The other method is that's the one that's being used for Gorilla Glass. Is that you do chemical strengthening. So assume that you make a glass that has small cations in there, like sodium, for example. And then you replace the sodium by ion exchange with potassium, which are larger. That way you put the surface under compressive stress again, and it closes so it has the same effect as tempering. Now, if you do that before there are any surface flaws in there, then you get Gorilla Glass. Right? And so the technology that they use at Corning is this one. This is a video that you can also see. I mean, I'm going to, in the interest of time, I'm going to just point out what's shown here. You can find this on Googling whatever Corning Gorilla Glass fabrication. There's a trough up here. The glass is melted and then it sort of enters this trough, and then it overflows on the edges on both sides, and it runs, and this is made out of platinum, it's very expensive. Then it runs and sticks to the wall, and the two sides now combine. The thing is that the surface of the glass, as it ends up being, has never been in touch with anything else. Right, so it's a very pristine surface, and then the ion exchange happens, and you get that really strong glass that you have in your devices. So I think I'm going to stop here. There's another video that you can look at from Corning, what they call the glass age, but I'm going to stop with this, just in case you didn't know. 2022, as per decree of the United Nations resolution, was declared the year of glass. It's over now, but now now you know. So with that, I thank you for your attention, and I'm sorry it's taking a little longer than expected.
Okay, thank you very much, John. There is a little bit of time left for questions. We'll get that set up. Start in just a moment.
Collecting glass bottles.
You're collecting glass bottles?
Glass bottles are hard to find.
Oh.
You said there's a gold in it.
Yeah, if it's this ruby red.
Is that what makes it red?
The gold nanoparticle has a particular kind of red to it.
Okay.
It's very brilliant red, like very.
Running.
Okay.
All right, we have a microphone. We should have two microphones. All right, there's one microphone. It's on this side of the room, so if you'd like to ask a question, go to the microphone. I see we already have. Right behind you.
Is my understanding
No, there's a microphone right behind you, but there's also somebody who's going to ask the first question.
So I was wondering, you're saying that the head of the Prince Rupert's drop is really strong, but the tail is weak. So if you were to say, like, melt off the tail, would you then have just a stone almost as hard as a diamond?
The short answer is no. So the tail is as strong as the head. It's just that it's
turn the
easier to
microphone volume
bend
up.
something thinner.
Turn the
And so you can break that more without, I mean, it's called the moment of inertia. So the thicker the cross-section, the harder it is to bend. And it has the same strength as the head of the tadpole. And it's not as strong as diamond. It's pretty strong, but not as strong.
Okay, thank you.
Thanks for the question. Sorry, I saw you had your hand up many times.
Mine isn't really a question. It's just that the glass used in most automobiles is tempered. And in the event that you should go into a river or something, you will not be able to break it easily unless you have something with a very, very sharp point.
Yes, thank you for that comment. They sell these little hammers, and if you drive by rivers on a regular basis, get one of those hammers to put in your car.
Go ahead.
Thank you. I was wondering what the blowtorch is for.
The what?
What the blowtorch is for.
Oh, I think we skipped that. I was going to demonstrate with that the glass becomes conducting if you heat it up. And that's based on ionic conduction in there. And it's good enough to have the bulb glow. That was would have been the justification for the chemical tempering or the ion exchange, but I was way past time, so I apologize.
Let me ask a question that comes from online. And it's about sand, actually.
Sand?
And glass. And the comment is, or the question is, that it's said that sand and glass are the same thing, at least chemically. So why are they so different?
Well, so the sand has constitutes some of the components of glass. So the chemistry, this is a physics lecture, but now I'm going to talk about chemistry. Typically what you have with a glass, you have what's known as a network former and a network modifier. So there's these two things that you would have to have. What you have on the beach is basically silica with impurities in it. So silicon dioxide is the sand that you find in most places. It has already impurities in there, but by itself it wouldn't melt well. So you put in say sodium oxide and calcium oxide. Sodium oxide and those things, they lower the melting temperature. Remember that eutectic diagram that I showed you in the beginning? So adding potassium oxide or calcium oxide to that lowers the melting temperature. So you can make glass at a lower temperature than whatever they did for the Louvre windows, like for the pyramid. So you can actually make it without burning the furnace down. And then the third component, so sodium is the modifier. It breaks up the network. So it's just where you have a silicon bond, sodium goes in there and said, I'm going to give you an extra oxygen. So there's now a silicon-oxygen, sodium, oxygen, silicon. And that sort of makes the network flowable. Calcium put in there, calcium has a higher field strength, cation. It sort of keeps the network together when you have a solid. So that's sort of like, so your window glass is silica about 70% to 75%, sodium oxide and calcium oxide both about 15% or less than that. That's what you have in your windows, typically.
I understand when the Chinese culture developed, they liked their ceramics, and it was not transparent. And as the wise men got older, their eyesight became poorer, and they had less time of their wisdom being shared in their culture. Of course, the Europeans didn't develop tea. They came up with fermented things like beer and wines. They're clear. And somebody discovered somewhere that you can extend reading ability, and they extended their wisdom out years and years. You become older, you became wiser. It wasn't molecules, it was science. Does that make understanding?
Sorry,
Well, you can, the Europeans made things that you can see through,
yes,
and they're transparent and extended their lifetime of wisdom.
right, okay.
Thank you.
My question also has to do with the transparency of glass. I was wondering, you sort of talked about the Louvre and how they had that very transparent glass that lets a lot of light through. And I was wondering, what is the main difference between that and the sort of the glass from the medieval period that was not as transparent? Is that mostly having to do with the purity of the silica, which I think you mentioned, or also the manufacturing process being a little less precise?
It's both, some of both. So in the early days, people didn't know what I was just saying, that silica plus sodium oxide and so forth. They just found by serendipity that certain minerals were able to be melted and then poured into mold, and you get a vessel out of it. What can happen is that you have impurities that are chemically impure, which gives you these color centers that I mentioned, like the transition metals that give you green, brown, or blue glass. Cobalt gives you blue glass. The other thing is the process may not have been allowing them to heat it up sufficiently to melt all the minerals, and so you have inclusions in there. That would be typical for glass of that age. And then after the process, if you have a mineral or a composition that's not a good glass former, then you produce something that starts to crystallize partially. And one of these things, which is actually intentional, I don't know whether I can expand on this question. You're familiar with actually, the Corningware, the brown fireproof container or pots and pans so they have a brown color, and that's actually not. It looks like glass. It feels like glass. Tastes like glass. I don't know, but that's mostly crystalline. But the crystals are nanoscopic, and they're so small that it doesn't interfere with light, and that it doesn't scatter the light, that multicrystals, but it's actually not glass. And it's yeah, so there's crystal inclusions and so forth.
Okay. So am I right then that does the presence of crystals make it not glass?
So yeah, that's right. That's by definition. If it's a crystal, it's not a glass. But you have what's known as a glass ceramic, which this Corningware, for example, is an example. What in terms of optics, when you have crystals of almost micron size, so a quarter of a micron, then that you can see scattering from the surface of all these crystals, and that makes it opaque. So it typically turns milky at that point.
Okay, thank you.
Another online question about glasses under extreme conditions. So going from a automobile window to a deep sea explorer vehicle with glass. What's the difference? Is there a difference?
So the glass that's being used for high pressure environments is typically thicker, but of course also tempered, so that you have any cracks that would exist on the surface would not give rise to a failure from that point of view. But other than that, if you just need to sustain higher pressures, you make the glass thicker. That's the short answer.
We have more questions in the room?
So I'm curious as to what the modern day research is like. Is this more like a theoretical math perspective in terms of solving equations to find new materials? Or is this more experimental research still?
You're asking about the modern scientific approach to glass science?
Yeah,
yeah.
You
So
say it was very serendipitous to find these new materials in the day.
right.
Now we have AI to solve more complex material equations just for the periodic table in general.
AI will solve it all. But the pictures that I showed you about the two structures, the one on the right that was a glass, those are generated by what's called molecular dynamic simulations. So they were introduced roughly in the 1970s to 80s, where people, previously they were doing experimental work on glass. And when that came about, there was like a shift in perspective on what glass structure really is. Now there's still some limitations to that, but computer simulations of the glassy state and glassy processes, that's one thing to add to experimental techniques. And then AI is something that's relatively new, but we are exploring that too. AI is typically more used to find specific properties at this point, saying that I want a glass with a certain viscosity behavior. Then you would sort of like relate AI, use AI to find what the composition should be, for example.
I guess another question is this related to like the fine structure constant, for example?
The what?
The fine structure constant?
Fine structure constant?
Yeah. It's like
I guess not.
37 number.
What's the question about the fine structure constant?
It's like when you're studying crystalline structures, like electron microscopes, for example.
The strength of materials, I think, is in essence the question.
Sure. Or like, what's the mathematics behind this? Like when you do a simulation, you need the math to run it on a computer?
Sure. I mean, if the molecular simulation methods, they're just based on solving Newton's equations of motion, or kind of making interactions between atoms and see what evolves from that. That's what it's based on.
So it's like Newton's equation still?
Yes.
Okay.
Yeah.
That's
Or if you want to do like certain glasses are semiconductors, you can also do density function theory calculations on those.
Okay.
So we're getting close to time. If we could get to the last couple of questions here.
Yeah, my question was simply, we're talking about how glass, when it fractures, it starts at an imperfection. So my question was, if you were able to make glass that had no imperfections, would it theoretically be almost indestructible?
Thanks for that question, but that's basically what Gorilla Glass is. It's almost perfect, right? So the trough that overflows and it forms like the surface of the glass, the two halves join. What's on the surface has never been exposed to any kind of friction, or the environment is controlled, there's no gas approaching it, then it gets immediately ion exchange. So you make something that's almost a perfect glass, the surface will be very, very smooth. It's not going to be indestructible. Right? There's still a tensile limit to any kind of bonding in materials. It just makes it much stronger.
Okay, thank you.
And the last question.
Do you believe that Tiberius' story is true? Notice we don't have valuable glass.
No, there's a slight chance that he discovered the resin, this artisan. But I think what happened, since it's like by word of mouth for 400 years, this was the time when glass blowing was introduced in the realm in the Roman Empire, right? And so I think that my interpretation, my guess is that there was a glass blowing demonstration, and so there was a bubble first, and then he kind of like dented it, and then he blew it out again or whatnot, and probably he didn't get beheaded for that. Unless they were saying that, oh, glass, no, I'm into metals. That could be the case. I don't know. But I think it's just the translation or the passing on of the first demonstration of glass blowing. That's in my opinion.
All right. Well, thank you very much. Let's thank Professor